Welcome back to Class 6. This is the last example I'm going to go through over. This comes from Cengel, and we're going to notice when we get to this portion here, we're going to actually find that our book does something different than Cengel's does, so it's going to make it a little more complicated. Anyway, we want to find the pressure of a water vapor at 600 degrees Fahrenheit and this specific volume. Using the steam tables, ideal gas law, and then the generalized compressibility chart. And because we don't organize ours in Bornacki this way, it makes it kind of a difficult one to try to do. So anyway, if we go to table A.2 for water, or Bornacki, somewhere in here, yep, there you go, we have water. So we have a critical temperature and pressure, 647.3 and 22.12 megapascals. This is the critical point. So we will find that the critical temperature is 647.3 degrees. I just wrote, why did I do that? Oh yeah, because we need, I gotcha. We need to be in degrees Fahrenheit, and yes, sorry, we're in English units. Losing it, 1,165.1 degrees Rankine. And I think we could just go ahead and look this up in F, right? We can go to F.1. Let me check that. Yeah, here's F.1 out of our book, 1165.1 and 3208 psi. Actually, psia, degrees Rankine. Okay, good. I'm not sure why I did that up here. Oh, forget about that. 3,208 psia. Out of A, I said out of A5. Made me a liar. Let me go to F. And where are you? Where's water? Oh, it's steam. That's it. Okay. So for steam, I don't know why they said water in the other table. Steam. Okay. We have 85.75. That's all we need. 85.75 foot-pounds per pound mass. So let's see. Must be F.1, I think. And this is table F.4. I don't know what happened in between those two. Okay, solids and other things. R is 85.76 foot-pounds force per pound mass degree Rankine. And if we go to the steam tables, so that's going to be table F.7.1. And that's 600 degrees Fahrenheit. Good. Let's go to the next page here. 600 right here. So we're going to come down this index, go to 600. And you'll see here's your pressure. And here's your fluid volume, and here's your gas. So here you get 0.02376 and 0.2676. So that means that it must be superheated. So at T equals 600 degrees Fahrenheit, PSAT is equal to 1,541 psia, and VG is equal to 0.2676 cubic feet per pound mass, which is less than this. So therefore, that's less than the VG given. Therefore, superheated. Remember, it's the inverse of density, so this thing is way less dense than this. So it must be more steamy. So if we go to table F.7.2, and it's probably going to be a lower pressure than this, so we don't need to go much further up. But if you check at 1,000, and it's at 600 degrees Fahrenheit, we'll look and see that we got 0.5140. That's exactly, right? So we could just say 1,000, right? We don't even have to interpolate. But we might have to look at a bunch of other things and do some interpolation to find what the pressure is, but the pressure is 1,000 because it matches. Yay! At P equals 1,000 psia and T 600 degrees Fahrenheit, we have a specific volume that matches. So we're got some pretty high degree of confidence this is correct. 514, I could be accurate here, 0. That's darn close. Close enough. So this must be the pressure. Bump, bump, all right? Conclusion made. To determine the pressure, we have determined the pressure. All right. So in the next part of it, we can let go. We can use ideal gas law. So this was like probably A. B, ideal gas law. We already got the R. So remember PV equals RT. We know that because PV equals MRT. So we can just divide this volume by that mass to get that specific. So this is going to be RT over P. Oh, my bad. My bad. We're going to go P is equal to RT over V. R is 85.76 foot-pounds force per pound mass degree Rankine. The temperature was already converted. No, we need 600 plus 460. So that would be 1,000. No, yeah, 1,060 degree Rankine. I think I'm correct. And then the V, let's say it's given 0.51431 cubic feet per pound mass. Right, and you can go ahead and start canceling things out. Here's your pound mass, and here's your Rankine. That's gone. One of these 3 feet's gone, so it's like 2. All right, so you got pound force per square foot. Sounds good. We're gonna get 1.7675 E5 pounds per square foot. So we would divide by 144 and get 1,227 psia. Compare that to the 1,000 that we just got, and there's a 22.7% error. All right. So the next part of this is a little bit difficult because we almost have to kind of treat it a little differently, right? So it's in the book differently, or it's in the other book differently right here. We're going to have the generalized tables, but first we need the reduced temperature. So we're going to get 1060, that's the 600 in Rankine, divided by the critical 1165, so we're really darn close, 0.9098. And here's where things get weird. We can look up what the critical volume is going to be. It's possible out of the first table in there. And this is for water, right? This is for water. Huh. We don't get the same thing. Is that? That's interesting. I would have picked that would be the same thing. It's the critical volume. Interesting. I don't understand that. Is what they say to do in the other book. I don't know if I want to go any further. Yeah. We could do this. Is it possible? We could estimate what the pressure was. No, that wouldn't make any sense. See, my problem here is that this is what Bornacki has to give to us, but I'm going to show you the other figure. All right, so one of the biggest differences you're about to see is that this right here is a log scale, whereas here is what they do in Cengel. We have, there's only from 0 to 1, right? Compared to, so that's only in this range from here to, well, they don't have a 0 here, but it's like for this range right in there. That's what they, this is what they have got going for them, right? So there's a different kind of like arc to it because, you know, this gets stretched and this gets shrunk. And then here you go. So here is closer, but it's still only up to 7, whereas ours goes up to 10. But once again, all of this gets shrunk together. And I think the arc that you see kind of right in there is what's being much more pronounced. You also have interestingly enough, you have, let's see, here you go. You have reduced volume there as well. So we have reduced temperature, reduced pressure, and we also have reduced volume. And we don't have that in the chart in Bornacki. We have this right here. We don't have any of those reduced volumes. And so what this problem was doing was using reduced volume. And they did something they called like the pseudo reduced volume, which I kind of thought that we should be using, you know, for this reduced volume, that you would go V over VC, and then this is the VC that you would be looking up. But that's not what they did. They went in ahead and they found the critical volume by taking R times TC over PC. Now you would think that this value would be the same one that you would get out of this table right here, this volume right here, because you have the critical, these are critical temperature, critical pressure. You'd think that your critical volume would come out from that right there, but it's not the same. Remember this, I said this is for water, and this is 0.0508, but in the textbook what they calculate right here is they use 85.76 and 1165.1, and to get the units correct they take the 3,208, but they multiply it by 144. What they end up with is a 0.2163 cubic feet per pound mass. And then with that, they find the reduced one of 0.51431 divided by what we just found, 0.2163. And they get 2.378. And then they look up the Cengel table for those two parameters, right? We have this parameter and that parameter, and then look them up. I have to kind of zoom right in there. And so if you have, let's see, I'm going to try to find it. Here's your reduced temperature, tracing down. Sorry, the thing is blobbing back and forth. Where is it reduced? All right, so here is the VR of 2.378. 2.378. We're getting really small right in there. So maybe we want to come back up into here and okay, so here's our reduced temperatures, and if you follow this down right here, you can see here's reduced of 1, and we needed 0.9, so here's 0.9, and then if you're following with the 2.37, here's 2.4, so here you go, right there. It's kind of right about where they're intersecting. Boy, this thing's really freaking out right now. So you can see, hopefully, that with that 0.9, and where'd you go, 2.47, somewhere right in here, they estimate that this is 0.33, but you can see there's 1, 2, 3, okay, 0.33 is what they have approximately at the reduced pressure. So the PR is approximately 0.33, and therefore our pressure is going to be that reduced pressure times the critical pressure, right? It's going to be PR times PC. So 0.33 times 3,208, or 1,059 psia, and compare that to what we found out of the steam tables, which was 1,000, right? So we have a pretty good match. It's like a 5.9? Yeah, 5.9% error, which is acceptable. But unfortunately, this example doesn't work in our textbook because Borgnacki doesn't have this figure in it. But I figured I put it in the notes that I would follow through with it. The end.